Hello, here we would talk about the fits and limits concept. It works where we have to assemble two parts together or we fits one part into another part like a hole in a shaft. And to achieve this designed value, we have to go through these different processes uh, like lapping, honing and rimming, then turning, broaching, boring. And here we define these tolerance grades for the turning process we could achieve the tolerance grade from 7 to 13, and for the drilling operations we could achieve this tolerance grade from 10 to 13. And the fits and limits are categorized in this way in NC American National Standards 4.1. This RC denotes for the running and sliding fits, and the locational clearance fits we denotes with this symbols LC. And then the transition fits with denotes with LT, and the locational interference with LN, and force and chilling fit with FN. And here we have some graphical representations of the hole and shaft tolerance with ASN NCB 4.1 standards in different countries. It follows different standards of its and limits, but the concept of designing the fits and limits values are the same. It's a center line, which is the basic zero line, and the upper sides, the grades we could see. It is for RC, which is running and sliding fits, and the tolerance grade you could see here are 1, 2, 3, 4, 5. As we goes down from this higher tolerance grade, we goes down, the tolerance goes tighter, and the downside you could see this black squares or rectangles are for the shaft tolerance, and then the clearance locational feeds and the transition feeds. Here is the this table that we use is to find out the values for the feeds. So the this running and sliding feeds we use is where we have to slides one parts into another parts. A very good example is of a shaft, or I can say the piston in a cylinder. So when we uh, define the limits and fits for the this mechanism of cylinder and the pistons, the piston moves inside a cylinder, and we have to consider the air gap between both this the wall of a cylinder and the piston. So for this air gap we have to try to achieve this RC class 3, which is running and sliding fits, RC3 or RC4, and RC2 and RC3, and we ends up with RC4 and RC5. So to achieve this RC3 value, all these numbers are given here in thousands of an inch, and here the nominal sizes are in inches. So for an example, if I say in this table that the size of my cylinder is 1.5 inches, so then I goes here for the running and sliding fits, which is of tolerance grade with 4. I can see over here the whole upper size limit is 1.6 thousandths of an inch, and to get the values in mm, I will multiply this 1.6 with I would divide this 1.6 with 1000, and then I multiply with 25.4, which gives me a 40 microns or 0.04 mm. I can go for the hole within this tolerance range. Next table is of locational clearance fit. Uh, and I have this table of locational clearance fit from 6 to 11. Locational clearance fits we use is where we have to fix one part into another part where we don't have too much clearance in the parts. And here you can see if the sizes of between these normal ranges, then the upper side we can say the size, the clearance is the allowance that we provide. uh, this is the mmc of the hole minus the mmc of the shaft, and this lowest clearance is the lmc of the hole minus lmc of the shaft. So this upper value we call it allowance, and the downside, this value we call it clearance. And then force ensuring fits are those fits when we have to fix one parts into another parts. We denotes it with the fn, and here in this table I have this tolerance grade of fn to fn5. So it's we can say this interference fit, and yeah, this upper size is the interference and the lower size is the maximum interference. So the very good example of force and the shrink fits are when we have to fix one bearing in a shaft, or for the interference fits, we could say the fixing of a bearing in an axle of a vehicle. And then in this ASME section B4.5, the preferred metric fits and limit systems, we uses these names instead of running and sliding fits or locational clearance fits with these three names: clearance, transition, and the interference fits. And these letters, the capital letters we use this for the whole, and these small letters we use this for the shaft. So it's there are two types of these tolerance systems, which is one is the whole basis fits and limits, the second is the shaft basis fits and limits. And for these go gauges and the no go gauges, we goes with uh, the gauges we design to inspect the parts, the plug gauge or ring gauge to inspect the shaft, and the pin gauge to inspect the hole. We go with mmc of hole and mmc of the shaft with go gauges, and we uses the no go for the LMC of the shaft and the LMC of the hole. And then further gauges are these are according to Taylor principles in the workshop. In a workshop area, we have different gauges, and gauges are differ from the workshop area, which we uses in this inspection. So inspection gauges are different than the workshop gauges, and the gauges values, tolerance values we get when we divide the tolerance values with 10. And here it's ASME section B4.2, and the metric transition and interference fits. All these values here given in the mm. So for an example, if I say the basic size is of 40, then for whole, if we talk about the locational transition fits, we can denote it with this K7, and the values is this 40.007 is the MMC, and this 39.98 is the LMC. And for shaft, which I can denote with H6, so this is the MMC, and 39.9 is the LMC. And here in this British standards, which also follows the metric ISO limits and fits, we uses this different grades, and we call it this IT tolerance grades. And the same for different process, we have these different grades, like in boring or in milling operations I can achieve from IT grade 7 to 11. And here we have a formula given in ISO system to calculate the IT grade. So here, if for the IT grade 7, uh, I will say it's IT grade 7 here, and IT grade 6 is here, so 1, and I will get the value of K is 16. So the tolerance in mm will be the 16 into I, and the value of I will get from here, it's 0.45, then cube root of D plus 0.001 D, where D1 and D2, these are the nominal range sizes. And from here we get the value of I, and when we multiply this value of I with K, we get the tolerance in mm and the fits and limits here in the British standard systems, which is of ISO metric system. Here you can find out the IT grades numbers, and these values are in thousands of mm. So after getting this IT grades number, we could define which process we could use to achieve that size. We can hit the values for a particular shaft or hole or fit. And here we have these selected fits, maximum and minimum clearance of British standards. All these are in mm. These dimensions are in mm, and these dimensions here are in thousands of mm. While in, if we see these tables of ASME section B 4.2 of metric systems, we'll see these values even are given in mm, not in the thousands of mm. So here we have these letters, which is of L11, C11, H9 to D10. These combinations are of interference fit or clearance fit or transition fits. And here again we have these same. It is for shaft. These letters we use is for the shaft, and here these numbers are in thousands of mm.